Good morning, everybody. So I think this presentation should have been done by Professor Juang, but he is not able to arrive on time, so I will make it. I'm a PhD student at the National Cheng Kung University in Taiwan, and I'm also system engineer on the QB50 Phoenix CubeSat. I'm going to present you the additional payload which we are developing at NCKU, which is solar UV probes. First, I will give you a quick overview about what kind of satellites NCKU has been working on, and also explain you a little bit more why we want to study the solar UV. I will present you the probe and how we implement this probe in the QB50 mission. So NCKU has been developing nano and micro satellite for more than 12 years now. The first one was space, platform for attitude control experiment, a 2-unit CubeSat started in 2002. It has been going on and then put on a pause and then started again, and actually it has been launched a few months ago. We have also participated in the ESEMS satellite, which was a Taiwan-Russian collaboration. So we have developed some subsystems for this satellite. We have designed the LEAP low-frequency earthquake precursor satellite. The goal of this satellite was to verify the theory we can detect earthquake, predict earthquake by looking at the low frequencies coming from the Earth. And the QTEX microsatellite, which has been fully tested and fully functional. It has not been launched, but in case if we would like to launch it, it is ready for launch. Then now we are working on the Phoenix, so we present you one of our payload of this satellite, and also on the Birdie mission, which is a CubeSat for a Mars mission, which I will present on Thursday afternoon. So, first of all, why the solar UV and what it is? So the wavelength is in the range of 10 to 100 nanometers, and actually it is generated by the solar corona, and it is absorbed in the upper atmosphere. The thing is that the solar UV and the X-rays are actually the most important implement of energy in the thermosphere. So it has a strong impact on how the thermosphere will vary, and it will also have a high variability, which means, for example, it has an effect on the radio waves, on the way the reflections, on the way the radio waves are reflected in the atmosphere. Also, the solar UV changes the density of the atmosphere, which has an effect on the drag, atmospheric drag, satellite reduced schedule, deorbiting, and space debris. So we think solar UV is something which needs to be investigated more, even if it has already been investigated. Usually it is studied using a photometer or a spectrograph. Both are optical instruments. And those instruments actually are more precise what we propose. We do not plan to revolutionize the science of solar UV. We just want to propose relatively simple and relatively cheap instrument, easy to implement, with which we could look at the variation of the solar UV intensity. So we do not get precisely the values of the solar UV, but we can look at the variation of intensity during the mission. So how does it work? It is very basic. We use a photoelectric effect. So basically we have on our satellite, on two of the sides of the satellite, we have two electrodes on each side. when the solar UV hit the electrode, secondary electrons, photoelectrons, are produced. And this is what we are looking at. We are looking at the variation of this current which is produced by the secondary electron. We are using electrodes which have different materials, because for each materials, what we call the work function is different. So the work function is the limit value of energy range to which electrical current, a secondary electron will be produced, and electrical current will be produced. Which means for different materials, we can look at different energy, so we can look at different wavelengths. So this is why we put two different kinds of material. So this is the engineering model of the instrument. So as you can see, it's a very simple experiment. So we have 4 electrodes. We amplify the current, and then we filter and we digitalize the value that we send to the onboard computer of our satellite. So this is a PCB board, you can see, and the electrodes. So the electrodes which are located outside on the panel of the satellite. So to test it, at NCKU we have a space operation plasma chamber in which we placed deuterium lamp. So the deuterium lamp is used to simulate the solar EUV incoming, and we put each electrode in the chamber. So then what we do is that we turn on the lamp, and by hitting the electrodes, secondary electrons will be produced, and we can monitor the electrical current. So here you can see on the left you can see the chamber, and on the right you can see the deuterium lamp, which we moved, and we hit each electrode, and we check the values. So this is, for example, what we obtained. On the left side, this is the current which is detected when the deuterium lamp is still not on, still being heating. So in that case, there is a current which is actually due to the electrons hitting the sensor in the chamber. But then when we turn on the deuterium lamp, we have a sudden increase of current intensity, and this is what we will look also when we will be in space. We will look at this change of current intensity. So in Phoenix, actually, so Phoenix is part of the QB50 mission, and we are going to carry the INMS, Ion and Neutron Mass Spectrometer, and the thermistors, which are both one of the part of the science sensor set of the QB50 mission, and we have our solar EUV sensors. So what we want to do here is that we are going anyway to carry the INMS, and we are going to look at the components of the atmosphere. By adding this small payload, solar EUV payload, we can have a better knowledge of the cause-effect relationship between the incoming solar EUV in the atmosphere and the constituent of the atmosphere. Because then we can gather the data which we will have obtained from INMS and the one from solar EUV, put them together, and see if there is a correlation. Actually, we know already that there is a correlation, but we do not know exactly how it works. So by this, we will look at the change of intensity of the solar EUV on the satellite, in the atmosphere. I will not go into details in this. I just want to say that actually it is very easy to implement, and that if we will have the solar EV payload or not, the system configuration will almost not be impacted. So, to summarize, because the solar EUV have a high variability in the atmosphere and is a major energy source of the atmosphere, we think it is interesting to be studied. And also, it will maximize the science return of the QB50 mission. We already look at the atmospheric component, so why not looking also at the solar EUV intensity? So, this instrument, we think, is a very good instrument to implement for the QB50 because it's small, it's light, it's relatively easy to implement, relatively cheap. It can also give a good training to the students, and it can be a good additional payload to have with the INMS. So right now the solar EUV has been designed, prototype, and also partially tested. So tested in the space plasma operation chamber, and we also had some pre-mechanical and pre-thermal and vacuum test on what we call the Phoenix table satellite, on which those solar UV sensors are implemented. So, thank you for your attention, and if you have any question, please.
Very simple technique of measuring extreme UV, which fits in the CubeSat. I wonder when you did the testing, did you emulate the UV fluxes, the extreme UV fluxes which you expect in space? Question number one. And the second is how this photoelectron current measurement will work in the plasma environment. Especially, I don't know if you embedded your electrodes in the plasma on the vacuum chamber we use there, but in space, I wonder how this will work and if you did some testing for this.
Okay, thank you. So to answer your first question, for now, the only test which we have done to simulate the solar EUV flux was using the deuterium lamp, and we know it is not exactly it does not cover all the range of solar EUV we would like to observe. So we still have, of course, further tests to do with a different incoming flux. Yes. I hope it answers your first question. And your second question was yes. So because the electrodes will be in a plasma environment, we know we can detect electrical current due to electrons and ions. So what we do is that we put a negative voltage on those electrodes, and then what we are going to look is really into the variation of intensity, because we expect to have a relatively stable current detected due to the plasma environment, but what we expect to have a sudden increase due to this solar EUV hitting the electrodes.
Any other question?
I would have one small one. Is there a particular reason why you implemented here?
Yeah.
Why you have implemented the multiplexer in front of the ADC converter? Because in terms of avoiding single point of failures, it would be easier to either put a 4-channel ADC or 4 separate AD converters.
Okay. actually, this is what we have implemented for this engineering model, but it is indeed something we are also looking at to potentially improve this instrument. Yes. Thank you.
No more questions? So then, thank you very much for the presentation.